Hey everyone, I'm Ollie from Campervan and this is part 2 of the Renogy Inverter Charger installation video. So in this video, part 2, it's a continuation of part 1. So if you haven't seen that one, I suggest going there first just to have a look. This video will not cover anything to do with setting up the inverter charger in regards to the settings and things like that, and actually installing the inverter charger inside the van. It's already installed. So what this video is going to cover is a complete overview of how we've installed the inverter charger in regards to the fuse boards, RCD protection, the circuit breakers to supply the inverter charger. We're going to go a bit in depth with earthing, and then what I'm going to do, I'm going to show you how it all functions. So I'm going to get it hooked up to the power and then turn it all on, do some tests, show you what happens there, and then also switch the inverter on without the hookup and do some testing there to show you exactly what's going on. And then after all that, I am actually going to show you how you can get an RCD to work on the outgoing side of this Renogy inverter charger. As I've said, it's center tapped. RCDs don't work on center tapped inverters, as I will show you in the video, but I found a way that it will work. I've got my RCD tester, my multifunction tester, so I can actually test the RCD to show you that working. So the information I'm giving you, I'm going to try and back up with regulations just to show you I'm not really just talking gobbledygook. I have the regulations here. Here they are, look. It's got a nice coating on it as well to make sure it lasts me. Ensure that you read the manufacturer instructions as well. I've got them here for the Renogy inverter charger somewhere. It's all been taped together because I've read it so much and ripped it apart so much that it fell apart. From front to back, just read every word so you've not missed anything. There are some issues and potential dangers actually in this manual that I will go through with you. So I do advise you do stick around from start to finish if you're installing this inverter charger, or you've got one installed and you need, I don't know, you want extra knowledge and help with anything. So by following this video, hopefully it's going to keep you safe and it's going to make everything work and give you peace of mind that all is good. So without further ado, let's dive in. So here's an overview of our electrical installation for the Renogy inverter charger. So there it is, obviously, that big unit there. And then this is our battery DC circuit here. And then we have two fuse boards, Fuseboard 1 and Fuesboard 2. So our entire electrical system is under here, so it's all accessible. This is our seat, so we've got a cushion on normally. Take the cushion off, lift the lid, and we can get to everything then. So it just makes it easily accessible. So if you've got to get to, an RCD or a circuit breaker or fuse or anything like that, or even just to get to the screen to adjust the settings, we can get to it easily. I'm going to start with the DC install and setup. So this is it here, this is the positive side. So we've got it connected directly onto the battery. So the inverter charger goes from the battery straight through to the inverter charger. You can take it to a positive buzz bar, so we've got our buzz bar there. If you do that, it just means you're going to need an even bigger cable from the buzz bar to your battery, because the inverter charger pulls a lot of amps when on inverter. So we'd rather it be the shortest route, which is to the battery. So obviously that's what we've done. So starting with the battery, you can see the connection's just under there. Then it comes out of there into our mega fuse. So our mega fuse is 200 amp because we've got the 2000 watt inverter charger. Now you must have a fuse. The fuse is there to protect the cable. So if there's any issues, whether it's overload or short circuit or anything, this fuse will blow and prevent the cable from burning out basically. That's what it's there to do. So you must have a fuse installed. The next thing, we've got an isolator. Now the isolator, all that does is turn on and off the inverter charger. You don't necessarily need an isolator, it's up to you really. The reason why we've got it is if we ever need to do any maintenance or we need to switch off the inverter charger if there's a fault or it's anything like that, we can turn it off there, literally just do that. And then it isolates it from the rest of the installation, so it's not going to cause any issues, or we can remove it or do work on it, anything like that. Obviously, if you don't have this, to isolate it, you've either got to disconnect the battery terminal, or you've got to take the fuse out, which obviously is held on by nuts. So you've got to get a tool out to isolate it. Ours is rated at 300 amps. We've got a 200 amp fuse, so we need this to be higher than the fuse basically, so it can carry the current. So we've just gone for a 300 amp. So from there it goes down here into the inverter charger, and you can just see the terminal right in the middle there. There it is. So it's right down there. That's our positive terminal for the inverter charger. And then the negative, which is this one here, comes out of that hole, goes up here, and it actually links onto, we have a negative buzz bar. We've got two actually connected together, but that goes directly to our negative buzz bar. Obviously the negative buzz bar then is fed from the battery and also goes on to our chassis. The cable connections, we've used lugs, so I don't know if you can see it very well in there. I'll put a picture up actually to show you what a lug is if you're unsure. It's down there. The bolts are M8. So what a lug is, allows you to connect a cable onto a bolt, which is what that is there. That's a lug. Now cable sizing, we have the 2000 watt inverter charger. We're using 35mm cable. If you go to the manual, each manual, whether you've got the old one or the new one, they all state that the 2000 watt you need 70mm cable, and the 3000 watt you need 120mm cable. So if you actually go to the cable manufacturers, a 35mm battery cable, ours, which I'll show you here, is rated at 240 amps. So that's more than enough. So a 2000 watt inverter charger is going to pull 167 amps at 2000 watts. Now a 35mm cable is rated at 240 amps, so that's more than enough with a 200 amp fuse to protect the cable. The 3000 watt inverter charger is rated at 250 amps at 3000 watts. Now a 50mm cable is rated at 345 amps, so obviously that's more than 250 amps, and a 300 amp fuse, which is less than the cable, to protect the cable. Now obviously these figures are based on the cable we've used, which I'll put a link to the description below so you can go and see that cable. But always go to the manufacturer instructions with cabling, because DC battery cables are slightly different in the amount of amperage they can pull. Now obviously your fuse needs to be less than the max rating of your cables to ensure that the fuse blows before the cable burns out. And then your isolator needs to be rated higher than your fuse to ensure obviously that this can withstand the power before the fuse blows. And the same goes for the negative. So our negative is 35mm as well. We've done cable calculations as well to work this out, because obviously the length of run, that's only short. But with DC install, you'd be amazed at how big the cable needs to be if you only extend it by a short distance. So always do cable calculations with any cable you install, just to ensure that the cable can withstand the power. Two fuse boards, as you'll notice, and both of these form part of obviously electrical installation that deals with the Renogy Inverter charger. You don't have to have two fuse boards, you can just have one. The reason we have two is because, well, reason one is we didn't have space to have it all in one fuse board. And two, I quite like the fact that we can keep the mains, which is this board, separate to the inverter output, which is that board. So it means then you can't mix circuits or anything like that, so there's no potential danger of things becoming live that shouldn't, or cross polarity with things through the inverter. So hookup is this board, inverter output is that board. So we'll dive into the hookup and DB1. Our electric hookup is here. It's actually on the outside of the van. There's a socket on the outside. This is a IP44 rated hookup plug, which is specifically designed for camper vans, so we've got that there. And then we've got a 2.5mm flex cable running all the way into here, DB1. The reason we've used 2.5mm flex, it's that black one there, is because we just had some left over. But 2.5mm is more than enough for supplying what we need here. So in the regs it does state that the first point of contact inside a camper van must be to an isolator, which is an RCD. It does say each supply inlet shall be directly contacted to its associated RCD, so that's the main incomer. And then it also states that it must not exceed 30 milliamps and break all live conductors, so that means double pole. So what that means is when this switches off, it's actually turning off the live and the neutral. It's not just switching one conductor like the live, it does both. Our RCD is 63 amp. That's fine. It doesn't really matter with the ampage with these. This is here for specifically for fault protection and isolating these circuits here. RCD is rated to 30 milliamps. Now that is in the regs and that is maximum in the regulations. So it can't exceed 30 milliamps. The reason for it not exceeding 30 milliamps is because that's what they kind of class as heart stop current. It doesn't mean you won't get a shock. You still get a bit of a shock, but it means that it's going to cut out before your heart cuts out. And the other note to add on this is RCDs have a type. Now generally RCDs are type AC. So what AC means is it's supplying AC circuits basically, which is what we have here. However, with an AC, it does state in the regs that only use type AC RCDs if there are no DC components plugged in. So here it is. So obviously type AC shall only be used to serve fixed equipment where it is known that the load current contains no DC components. Obviously nowadays, most stuff you plug in, like a telly, a laptop, anything like that, has a DC transformer basically. So you'll find that AC RCDs are becoming obsolete. So in a camper van, you must have a type A RCD and not a type AC. So what will happen if you have a type AC and plug in appliances and things that have they have DC components, it could actually affect the way that this RCD works. And type A's are a bit harder to find and they're a bit more expensive than AC, but you can find them, and I will put a link to this exact one in the description below. So obviously mains comes into the top, goes through the RCD, and then I think, yeah, I've got power on at the moment. So there is a test button on an RCD, and that means there's power coming in. So I've got the hookup connected. Now this test button here doesn't necessarily mean that this RCD is functioning correctly. What the test button does is just test the mechanism inside. So obviously that's working, happy days. And what you should do is test that every month, because they have been known to seize up kind of thing, and it can affect the tripping current as well. So obviously every month kind of put a reminder just to go press, and that's all you need to do. Do it a few times just to sort it out a bit. Following on from the RCD, this then feeds this buzz bar here, which supplies power to these two MCBs. So this MCB is what we're going to talk about on this one. This supplies the inverter charger with power. So this is the AC input. So this is our fridge, and we only run the fridge 230 volt. We're on hookup, which is why it's in this fuse board, but we'll ignore that for now. Circuit breakers in Fuseboard in camper vans must be double pole, and double pole means there's two switches. So here, so it's double pole, and it disconnects the live and the neutral, the same as the RCD. So it must disconnect both live conductors, so live and neutral. In the regs, you can see here that each final circuit shall be protected by an overcurrent protective device which disconnects all live conductors of that circuit. This isolator, you'll notice here, it says B10. So the B is the type. So type Bs are fine for camper vans. Some people do advise type C. Now what type C is, it can withstand a higher kind of startup current. So anything that powers motors, things that have a bit of a surge on them, things like that. Type B may trip out on startup. And then the 10 is the ampage. So we have a 10 amp. The reason we have a 10 amp is because our inverter charger is 2000 watt. So the ampage for 2000 watts is 8.7 amps. Now we're never going to use 2000 watts. I think the max we'll ever use is 1500, but for this unit it's 8.7 amps at 230, because obviously we're in the UK, so we'll base it on the UK. Now, America, I'll just cover America. So if you're running 120 volts, that's 16.7 amps. So obviously you're going to need a bigger circuit breaker than what we've got. If you've got the 3000 watt model at 230 volts, you're looking at 13 amps. And if you've got the 3000 watt model in America and you're running 120 volts, then that's 25 amps. So obviously you need to rate your circuit breaker respective of the inverter charger that you're using. Now you'll notice in the manual here that it does state, so obviously there's a 2000 watt model, 3000 watt, that there is a surge power. So the max surge power for the 2000 watt is 6000 watts potentially. Now obviously that's what it can withstand. It doesn't mean that when you turn it on it's going to pull 6000 watts. It all depends what's plugged in. So I mean 6000 watts at 230 volts is 26 amps. So it's going to trip our breaker out. Now the reason we've still got 10 amp is because we're never going to pull this amount. Now obviously to do the maths with these, if you're in America and 120 volts, is just divide the wattage by your voltage. So for example, 6000 watts divided by 120 gives you 50 amps. So you can see the difference it gives you. But obviously this all depends on the power you're going to be pulling through. And we've had our system installed for 2 years now with this breaker being in, and it's been fine. It's not tripped out, overloaded or anything, so all good. So from this breaker then you can see the cable there which goes out, which is this blue one. So the blue cable for us then routes round, and it's the input. I've just removed the cover for this now. That's the input side of the inverter charger, so that's the power coming in. Now we've used a 6mm 3-core flex for this. The reason why we've used 6mm is because we had some left over from another circuit, so we've just whacked it in. It's a big cable, we can fit it in, it fits in the breakers, so that's why we've used it. So you will get away with 2.5mm cable, as long as the run of cable is not too long. So do ensure you do your cable calcs with your volt drop and everything. But 2.5 cable is generally okay to feed this unit. So then from the inverter, the AC output, which is these three here, we've used the same cable, 6mm twin and earth again, and that runs out, you can see it there, and it runs into DB2, we'll call it. So what we have here, the AC output comes into the Fuseboard, we've got it coming in at the top, and it comes into here, into another RCD. So this RCD, the same applies for DB1. It's a 63 amp, 30 milliamp, because that's the max we can have, and it's a type A RCD. Also, it's double pole, so it means it powers off at the minute, but it isolates both live and neutral on the outgoing. So what will happen is the power from the inverter will come into here. Once that's switched on, we'll be able to press the test to check it works, and the power will then supply these circuits here. Same again with these switches, they're all double pole. These supply power to our sockets. So our sockets are these. So obviously we're in the UK, so we have 3-pin sockets. And then we've got multiple sockets spread around the van for different reasons. That's why we have 3 circuits. So a note on the Fuseboards, these boards we bought to sort of build ourselves. So this Fuseboard is classed as a 4-way. Now 4-way is 4 double pole ways, so there's 1, 2, 3, 4 double pole ways. Now that fills this Fuseboard. And then this one here, this is a 6-way. So obviously you can see we've only used 3 ways. That's a spare way there. But we have something else we need to install into here, which I will show you in this video. You'll need it for the inverter charger. So that's why we've got a 6-way. The other reason why we've got 6-way is because you can see that with the cables coming in, we wanted a bit of room, you know, they don't bend too well, these big ones. So it just gives us a bit of space to work. So next I'm going to talk about earthing. Earthing is going to kind of run throughout this video, but what I'll do, I'll show you exactly what we've got installed now, and then everything will become more apparent as the video goes on. So down here we have a main earth terminal. You might see it labelled as MET on drawings and things like that. This is basically the main point of bonding in the van. So what we have is this beastie here goes straight onto our chassis. Now in the regs it does state that anything bigger than 4mm would be fine in a van. The reason we've used 16mm is because it's kind of the biggest cable that will fit into here. We had some left over as well, that's another reason. Also, earthing acts as a fault path for fault current. Now the bigger the cable, the least resistance. So we thought whack a beast in and then there's no worries then, is there? So what we've also got is DB1 and DB2. One runs up to here, which goes onto our earth buzz bar there. So we've got that through, we've got a link to this one. And then this is the hookup cable earth, then this is the inverter input, and then that's our fridge. So everything is linked together through there. And then the other one runs to DB2, which is here. Same again, we have the output earth and then each circuit in order, just running through there. That's our neutral buzz bar, which I'll go into more depth in a bit. So the other two we have are bonding conductors. So these run to these pipes here. Now these are our underfloor heating pipes, and the reason we've got two bonds is because there's a rubber pipe here, and then where they run into our cupboard they're not joined, so we've just joined them there. We've got a bonding cable to our gas pipe as well, because that runs through a cupboard with electrics in. So again, I'll show you the regs. So predictive equipotential bonding. So it says the structural metal parts which are accessible from within the caravan shall be connected through main protected bonding conductors, that's the cable, to the main earth terminal within the caravan. So that's your chassis bond basically, this one here. And then another note on the chassis bond, it just states in the regs that termination is a protected bonding conductor connecting the conductive structure of the unit, so the chassis shall be accessible and protected against corrosion. Just to show you, this is the chassis connection. It's got a safety electrical connection, do not remove, and then we've took it back to bare metal, put the connection on, and then just put some rust protection spray on just to stop it corroding. So supplementary bonding conductors for exposed and extraneous conductive parts, which is like our pipe work, is not less than 4mm. Now in ours, again, because we had cable left over and things like that, rather than us buying 4mm, this is 6mm and these two are 6mm. But all of this you could get away with 4mm if you wanted to, which meets the regulations. The last sort of thing on bonding is this label here. So you must have a label, safety electrical connection, do not remove, at the main earth terminal. So a last note on earthing and bonding is this grounding section in the manual here. So it recommends to bond the inverter chargers to the metal frame of the RV. Connections must be tight, yada yada, and then the wire size for the grounding needs to be 8 gauge. Now 8 gauge is 10mm. So this grounding point we're talking about is there. You can see it next to the negative. It's that little connection there. You can't quite see the cable because it's dark, but that's it there. It's an M4 bolt, that one is there, and then our cable is 10mm, so 8 gauge, and what it does, it routes from there through the same hole as the battery cable up here, and it actually connects onto our negative buzz bar. So the reason we've done that again is we've got a big cable which goes from here down to the chassis. So this cable connects to the chassis via the negative buzz bar. Now we have been asked before whether you can combine this ground with this cable. So basically, rather than running the cable all the way to the buzz bars, you go straight from there onto the negative point there. You can, obviously, and it will be grounded because, well, it goes the same route, this cable does. However, it's kind of frowned upon. You shouldn't really mix a bonding cable or a grounding cable with like a supply cable. So if you ever lose the supply for any reason, this comes off or whatever, it's likely not going to happen, but you also lose your grounding point. So it's quite important to keep these things separate. So if there's ever an issue, you've still got one of these in place. So that then is our sort of bonding setup. We've been asked a lot, and there's a lot of confusion in regards to do you bond the chassis, you know, do you bond pipe work, things like that. For us, in our installation, for safety, yes, everything is bonded. So for that reason, if there's ever a fault in the cable or for us or anything, in regards to electric hookup with an RCD, it creates a fault path. So if there's a fault to an earth anywhere, it's actually got a path to trace back through, which will ensure that this RCD will trip out. Now, the issue comes when we start talking about this inverter and other inverters that are center tapped. Because as we know, or as you don't know and you're just learning in this video, that RCDs do not work on a center tapped inverter, even though we've got an RCD there. I'll go into that a bit later in the video. But what I'm going to do now is do some testing. So I'm going to switch it on and show you how it all functions. Let's do some testing. So the hookup's connected in. Power's on, so it's running down here. It's running into our RCD, which is switched on. So what I'll do is turn on the inverter, which does a beep and comes on. This is the state it will be in once you turn the power on. Now what I need to do is switch on from the actual remote switch. So turn that on, and then this light will mimic the inverter. Then you hear it beep. This will come on once the inverter's on. There we go. So now you can see that input voltage is 239, then you've got output voltage 238, and then here you can see it's in bypass, so that's the power coming in. This is the charger for the battery, so it's charging, and then this is the bypass. So what happens with the inverter charger, once it senses power coming in, which it has, it completely bypasses the inverter. So the power coming in is exactly what you get coming out. Automatic relay switch inside that does that. So what's happening now is power's going out of here. It's coming into here, and then the RCD, as you can see, is tripping. Happy days. So if I switch on, I can't remember which circuit it is, but I'll do both of these. So what I've done, so RCD's on, power's then running through here, and it's going to these two socket circuits. So here's the socket, and I've got a socket tester plugged in. If I switch that on, ta-da! So that means correct. So 2 green lights, as you can see there, is correct. So what I'll do now is I'll isolate the hookup just to recreate either an RCD that trips or hookup's unplugged or the breaker's turned off. And then what's going to happen is, because this has got that auto relay switch inside, when it senses there's no power coming in, it immediately switches to inverter. So what you'll see is the bypass disappear and switch to inverter. So I'll just turn the RCD off. There we go, and it's pretty much immediate. So now what we've got is no power coming in. Obviously input is 0, but the output is 229 volts. So obviously we're feeding off the battery, pulling 12 volts off the battery, and then putting power onto DB2 again. Now what I'll do is I'll do that. So test button. Okay, so back at the socket, same scenario. We have a problem. So what that is saying is live neutral reverse here. Obviously it's not live neutral reverse because we've just done a test to kind of prove that. Sorry, just turn it off. But that thinks there's a live and neutral reverse. Now the reason for that is, I'll take you back, the power coming out of this inverter charger, even though it's pure sine wave, and people will think that, you know, pure sine wave is the same as what comes out of your house. Technically it is, because you're getting 230 volts. But how this power is delivered is different to the power that we had before coming in, that I explained. Which is the reason why we're getting that reading, and I'll do some tests in a bit and I'll show you the reason why this RCD is not actually working. So this is the situation we had when hookup was on. So obviously this is your mains power. Comes in, it turns the relay on, So then the power comes through and goes to your load. So your load has got 230 volts there, which we saw. The polarity is good because your live's coming in, your neutral's coming in, and then the earth there links through, and it's actually connected. We'll pretend this is like a socket or something. It's actually connected to your socket. Happy days. What actually happened when we just switched it? So the relay is going to switch off because it senses no power coming in. Relay off. So I'll take that link out, take that link out, and take that link out there. So now, obviously, the input and the output are separate. There's no link there anymore. But what happens is, rather than this being 230, 0 and 0 like it was before, so we had live, neutral, earth, what we've actually got now is 115, 115, and 0. If you test between L1 L2, you're going to get 230 because you add up 115 and 115, just like we did here. So you've got 230 and 0, which adds to 230, which is why your load is going to work. So anything that's plugged in is still going to function on your inverter. However, if you test live to earth, we'll say this earth over here or this one here, you're going to get 115 volts. And then between this one and this one, so L2 and earth, you're going to get 115. Why is this? Now, the reason for this is called a center tapped system. So what's actually happening is there's like a link here coming out. So then if you measure between these two, you're going to get 230. And because there's a central link here, if you go between those, you're going to get 115. And between that one and that one, you're going to get 115 volts. Now it's got what they call a center tapped earth, so that will be like an earth there, and that's why. So they've moved the earth. So I've got it there on the drawing, but if you imagine it in the center, rather than it being separate here, it's in the middle. So you're actually reading 115. In America, I'll just quickly show you. So if you've got 120 there, you're going to get 60 volts here and 60 volts there. Kind of design really for America, because if you get a shock now from live to earth, you're only going to get a 60 volt shock. I say only, you're still going to get hurt, but it's 60 volts. Whereas for us in the UK, it's actually 115 volts. So I know it's not the same as 230, but it's still a decent amount. So what I'll just do some voltage readings just to show you exactly what's happening. So this is just a cheapish multimeter. I've got this because pretty much anyone can afford one, so it's easy to show you on something you can afford and everyone's obviously got. So you want to set it to AC volts, so AC is the squiggle, DC is the flat line there, and 250. So we're going to be reading 230 volts, and that's like rough maximum is 250. What I'll do is I'll go from live to neutral, which is quite high actually, which gives us 244. And then if I go from live to earth, that should give us the same, roughly, 245. So if I go neutral, what I'll do is I will go 0 from, now the reason for that is the neutral and earth are combined at the source. So the live you've got 230, the neutral is 0 volts, and earth is 0 volts. So exactly the same as before, same tester, same setting, volts AC 250, because we're still getting AC voltage coming out. And then I'll do the same tests again. So what I'll do is I'll go from live to neutral, which is giving me 236 volts. Happy days. So anything plugged in is going to work because it's getting 230. Now what I'm going to do is go live to earth, 114 volts, and neutral to earth is 120 volts. So if you add those together, you're getting 134, so it should roughly equal your live and neutral, which is 236. So that just shows you that this inverter is center tapped. Now you can do that exact same test for any inverter. I know I stated in part 1 of the video that when we actually bought this unit, we overlooked the outgoing power, and I didn't know it was center tapped, I'll be perfectly honest. It's something we didn't really look at, and they don't advertise it in bright flashy colours and headings saying this is centre tapped. They just don't. The question is it safe being centre tapped or unsafe? And the simple answer is it is safe as long as you install it how centre tapped inverters should be installed. And issue number one, sorry, I'll just go up to here again, is a socket. Now, I'm not sure anywhere else in the world, but in the UK you can get single pole and double pole sockets. Single pole socket, what that means is these are your live and neutrals here, and that's your earth. Single pole means it will only switch off the live. So when it's turned on, you're getting live, neutral and earth. When it's switched off, you're still getting an earth, but it's only isolating one of these poles, typically the live. With a socket on this side, you can see if it's just the live that's broke, let's just presume that this is the socket. If the live is cut, turned off, then you're not going to get a voltage through this because you've got 0 volts. So that's single pole. What double pole means is it cuts both the live and the neutral. So on this side, if you disconnect the live there, this will no longer be 230 volts, but you're going to have 115 volts at your load, even though it's turned off. So it's disconnected there, which means 150 volts can't get to there. Whereas this one, you're actually going to be getting 115 volts on line 2, and that's going to be turned off. Okay, so that could cause issues depending on what you're plugging in. So always use double pole sockets. So if you double pole it, or both line conductors, so live or neutral if you want to call it neutral, and then what you're going to get there is 0 because it's isolated them. So that's the UK. I know that if you just go and buy a socket, generally they're all single pole. You may need to search and look for double pole sockets, but we use Crabtree, and I'll put a link to those in the description below. The next thing I'll show you is what happens when power comes back on here. So before we do any testing or anything with the RCD tester, I'll just switch that on and show you what happens. So currently it's on, obviously, inverter, fan's on, hopefully it's not disturbing me too much. So the system is centre tapped, so it's powering our loads. Power's off here. Now what's going to happen is I'm going to turn this on, but this doesn't switch over immediately. It takes about 8 seconds, and I think that is so it's looking at the voltage. So when it sees power come in, it's going to sit and just make sure that that voltage is stable before it switches. I'll position you there, switch it on and show you what happens. So turned it on, you can see there it sensed the power, and it's just waiting to make sure the power's stable before it switches on. There we go. So now it's bypassing the inverter again, charging our battery, obviously that switches, and then I'll go over to this again. There you go, correct. So now we're running on mains again. So this is my tester. So it's a Fluke multifunction tester with an RCD test function. So you see the RCD test, specifically to test RCDs. So I've got it set to, let me zoom in a bit. So it's set to 30 milliamps to test 30 milliamp RCD. 1 times, which means I'm testing at 30 milliamps. And it's set to AC, because in the regulations now it just says whatever RCD you're testing, tested at AC. And the regs also says now that it needs to test in less than 300 milliseconds to pass. So I'm on hookup, so obviously you can see there it's in bypass. Power's on to the tester. There we go, 51.7, so that's less than 300 milliseconds. I'll do that test again, and I'll just show you here a bit closer, and you can see that obviously the RCD is on. If I do, there we go, 36.2. I'll turn it on. Now we're getting error. Now error 4, what that means is an issue in voltage, issue between the neutral and the earth voltage. So again, I'll show you what, if I switch it to volts. Now you can see here, what I've done is between live and earth, we're getting 112. If I do between live and neutral, we get 234. And if I do earth to neutral, we get 119. So that's where the issue is. It's getting a voltage between neutral and earth because it's center tapped. So 30 milliamp, test at 30 milliamps, AC, it won't let me test because it's in error. So that just shows that that RCD will not function as it should on a center tapped inverter. So I'll just briefly explain what's going on with these RCDs. Now, this is very brief. I'll be honest that RCDs and earthing and inverters, they need the whole own videos and stuff. So this is just a brief overview, okay? So what we've got here is the hookup is on. So 230 volts coming in. This is your bypass switch in your inverter. It's coming through and we have 230 volts and 0 volts. Happy days. And then what I've also done, I've put the earth terminal, so everything's linked. So that's the casing of the inverter charger, the chassis, and all earths, all the other earths connected to it. I've not included everything because I haven't got space. So basically this is a happy system. This is what's happening now. The other earth I will put in actually is the earth from here. I'll just join it to there just to show you a path. So we've got an earth to our load there. An RCD is looking for balance. So coming out, if it sees 0.1, it wants to see 0.1 coming back in. Now these two figures I'm just using as a pure example, just to give you an idea. So 0.1 comes out through, 0.1 back in, and it's more than happy to sit there all day. Now if there's a fault, you come along and you're touching this live here, and let's just link it. Let's say you stood on the chassis and then you're touching that live there. So this is you touching that. Now again, the RCD wants to see 0.1 coming back in, but because you're touching it, some of that is going to flow through you like we did before, then through the chassis, back through here, through this neutral to earth bond, and back up again. So you're part of the circuit. So again, let's say 0.5 goes through you, 0.05 goes through there. This is not the same as this, so then again the RCD is going to trip. Happy days. So then you're very happy that it's been isolated. So what happens when the inverter's on? So the situation now is the inverter is on inverter. So there's no power coming in. So obviously this bypass link has gone. The inverter's on, so we're getting 115 volts and 115 volts to the load. So what does that mean for the load? Well, the load's on, it's happy, 230 volts. Sorry, I've just included that earth there because that was missing before. Now, what's happening here is this is where we got this floating system. So you can see here there's a neutral to earth bond. Here, there is no neutral to earth bond at all within the unit. So you got 115, 115. However, you've still got all your earth still linked in. Obviously, that's not changed coming through. So what happens now if there's an earth fault? So let's say the appliance has an earth fault. It's got a metal casing. The earth's obviously on the casing. It's going to flow down here. But obviously now there's no way back. So what's actually going to happen here is this earth system is going to be at the same potential as that live. So with a floating system or center tapped floating system, it is incredibly safe because you've not actually got a fault path, which it obviously introduces shock risk. If you touch the live and the neutral, you are going to get a shock because then you're part of the circuit. However, if you touch the live and neutral in this instance, you're still going to be part of the circuit. So the RCD is likely not going to trip out because obviously what's going out is coming back in just via you. So the way we get an RCD to function on this sort of unit is by bonding the neutral to the earth, like so. So what happens there, so this bond is the same as this bond. So that's your neutral to earth bond and that's your neutral to earth bond. So what's going to happen is That's going to go to 230. That's going to go to 0, a live and a neutral, and then obviously the earth there is 0 volts as well because they're combined. Then we're still disconnected from here, and now you're getting 230 and 0 volts. So if we introduce U again, let's put U in, it's just a bit better in it. So you're touching the earth, you're touching that live. So the live's going to come through into the load and back through the neutral, fine, but some of it is down U to the earth again. If you follow that earth, there's now a link here, so it brings it back into the inverter. So it's actually flowing round that way. So that again is going to create an imbalance. Let's do 0.05 again, just to make it easy. 0.05. Obviously 0.05 is different to 0.01, so it's going to disconnect. Click, and turn you off, so you're not going to be zapped. So now you're probably thinking, happy days, problem solved, no issues. But what happens now if you put the hookup back on? So let's put hookup back on and see what happens. So that'll link to there, then the neutral links to there. So like before, so obviously hookup's on, RCD's on, the internal bypass is on. Obviously nothing happens here because it's still 230 and 0, so power's going to flow around lovely jubbly. The only difference is this link here. Now this is what's going to cause an issue in this system, because you can't have 2 neutral to earth bonds in one system. So obviously power's coming in, you've got 2 neutral to earth bonds. This will cause an issue for the RCDs, so it could involve nuisance tripping, or it could actually affect the tripping when this situation occurs, when there's like a live to earth fault or somewhere. So what needs to happen when on hookup, this needs to come out. So now we've got 1 neutral to earth bond there. RCDs are going to be all happy, fine and dandy. So what I'm just going to do is refer you to the manual that we had with our inverter charger. So this is version 1.1. It's actually outdated, this one now, but I mean our inverter charger is 2 years old, and it just says version 1 now. It's online, but I'll refer you to pages 13 and 14. This is where we were misled. Now this is what I've just explained. So neutral to ground connection in inverter mode, neutral to ground connection AC mode. So AC mode's on hookup, that's obviously non-hookup. So hookup, like it is here, you can see that the neutral in is linked to the neutral out. So neutral in, obviously neutral out. They're not connected to ground at all, which is correct. They're not connected to ground except for this point at the source here, which is before this connection. So when switching to inverter mode, inverter in and neutral out get disconnected, as you can see there, and they link to ground. That would be the situation if we turn the power off there, introduce that link. Now that is what that is there. However, when I installed it, tested it, RCDs didn't work, and I was like, what's going on? Tested the voltage was weird. Contacted Renogy, and they told me that this is not true. This is actually not installed in the inverter, and it's for like future. They're doing something in the future apparently with this. So obviously there's an automatic neutral to ground bond switch in the manual that isn't in the inverter. So think you're installing this for an RCD to work, which it will if this is installed, but you're not getting this, which is an issue. So I've been to and fro with Renogy for quite a few months now, which is why it's taken so long to do this part 2. And almost every reply has told me that you can't neutral to earth bond the Renogy inverter charger, the PCL inverter charger. I've been on forums looking around, and I found a forum, I'll show you here now, which someone has actually been in touch with Renogy, and they have stated you can do it. So you can neutral to earth link neutral to earth bond the inverter, but it must be removed when the charger is installed, like I've just shown you with the drawing. The only way to find out is to try, isn't it? So what I have is this. So this is a contactor. What this contactor is basically what I've just shown you in the manual. It's what that is. It's just external, not internal. So even though Renogy are telling me I can't neutral to earth bond, I've neutral to earth bonded it. Now I have neutral to earth bonded it. I've tested it. I've tested the RCDs. Everything works as it should. Everything seems fine. Nothing's blown, which is great. Now I don't know if it's going to affect the internal fuses or anything in the inverter. I can't say. Now it's already got cabling, so I've already installed it to test it to make sure it does work, and it does work. So what this does is, like on the drawing I showed you where you've got the neutral to earth bond, you would need it on the inverter side for the RCD to work, but you need to remove it when the power's on from the hookup. That's what this does. So I'm actually going to show you how to wire this now and how to install it. So I've installed it into DB1 because it's going to be fed off this circuit breaker, which was feeding the inverter charger. So obviously when that's turned on, the coil energizes. The power coming out of it also goes into the top of the contactor, which is into 1 and 2, so live and neutral. And then live and neutral come out of 2 and 4 into the inverter charger. The other connection we've got is the end one, the normally closed one. So we've got one going from the earth bus bar, and then the other end, which is that one there, goes all the way around and links to the neutral. So we've actually made a neutral buzz bar in here for DB2. So the neutral buzz bar, the outgoing from the inverter charger neutral comes into here, and then we've got a link from there to the RCD, which then this link goes on to. So the state it's in now is the inverter is on, the hookup is off. So currently the state of this is we have neutral to earth bond. And the way of showing you that is I will turn on the RCD, just give it a test. And I will turn on, I'm going to put on both those circuits because I'm going to be using those now. Go up to here, and there we go. So as before with the inverter, sorry, switch that off again. As before with the inverter, it came up as a live neutral reverse, whereas now it's correct, it's good. So to prove even further that RCD works, I've got my RCD tester here. So I've got it set to 30 milliamp, trip at 1 times, which is fine, and set to AC. So if I hit that, boom, tripped. What I'll do, I'll just test it on the other way as well. Boom, happy days. So reg state, it's got a trip in less than 300 milliseconds, and you can see there, 35.8. But that's just proved that that RCD is testing, and that test is to the regulations, so tick. Then what I'm going to do now is switch the hookup on, and we'll see what happens. So what's going to happen, I'll turn that on, turn the power on to that. Once the power comes on to that, this will flick on, so it'll open the bond we've got now, and it will close the contacts, powering up the inverter charger. So you may hear a click. That's on. We'll just see what happens with this. It takes a second to kick in. Here we go. So now the inverter charger's in bypass. So the way we had it before, obviously the RCD, trip the RCD out. That's going to work. And then what I'll do, I'll go up to here again. Correct, happy days. Just to do a bit more of a demonstration, what I'm going to do now is turn the socket tester on. Currently we're on hookup, so that's in bypass. So what I'm going to do, plug the tester in, I'm going to switch the hookup off, and we'll see what happens to the tester, and then I'll switch the hookup back on and see what happens there. Okay, so hookup's on, inverter's on bypass, RCD is working. I'll switch that on, which will turn the noisy socket tester on. So you can see there that it's on. So what I'll do now, I'll create a scenario where the mains turns off, this will turn off, and this will turn into inverter. So that's immediate, and you can see how fast the socket tester, there was no interruption at all. So it's now on inverter. So there's power's off here, and obviously we've still got power there. Trip that out. So what I'm going to do now is I'm going to turn this on. That will come on straight away. That will take a little bit of time. So let's switch that on. Contactor's on. So now you can see that the socket tester is actually in fault because it's in center tap mode. And there we go. Once it's in bypass, the RCD works. So it's functioning well. The only issue is that few seconds of time where it's obviously center tap mode. Oi! There we are then, guys. Part 2 Renogy Inverter install video. There's a lot to take in there. I do appreciate that, and anyone who's not an engineer or electrician or anything like that, I do understand there's a lot to take, but that information needs to be there really, because you can see the potential risks and dangers of installing not just the Renogy inverter charger, but any inverter really that's center tapped and stuff. I hope the video was informative. I hope it was all understandable and you can follow along. If there's any questions, comments or queries, anything like that, please drop it in the description. A lot of people aren't installing them because you can't use an RCD. This video and this install proves you can. So we're happy that we can keep the unit. So what I'm going to do, because I know there's a lot to take in on the video, I'm going to do a detailed blog post on our website, basically covering exactly what's covered in the video. But at least there'll be diagrams and illustrations and just simple explanations really, so you can just follow along. Do it safely, do it to the regs, get the right advice from the right people that have done it before and have got the experience and qualifications to give you that information, and I hope I can be that person. So thank you so much for being here. I hope I haven't bored you to death, and hope it's been informative, and I hopefully see you in the next one.